this point in the vector calculus series, we're going to start talking about line integrals. And I just wanted to give a brief overview because there are actually two different kinds of popular line integrals. One of them is a line integral through a scalar field, and the other one's a line integral through a vector field. And so those are very different, and they're calculated very differently. The idea of a line integral is we've learned thus far in this course, we've learned how to write parametric vector curves, in other words, r of t. So we've learned how to draw all sorts of interesting curves using vector equations. And now our goal is to figure out how can we integrate these curves. What use will it be integrating these curves? And so the difference is between a vector and a scalar integral is with a vector, or let's start with a scalar. With a scalar function, let's say that we have a function that has an x, a y, and this, we're not going to call this the z direction, we're just going to call it function of xy. And let's say that that curve, or not curve, but this surface that the function creates looks kind of like, let's make it look like some sort of a paraboloid. And so that is what our surface looks like that's created by this scalar function. And what I mean by scalar function is that for every x and y, we have an output f of xy. And that output might be 10 units high, it might be 20 units high, but each ordered pair in the xy plane has a value f of xy that is related to the ordered pair. And so the idea of a line integral in a scalar field is, what if we have some curve c? Let's make it kind of look like a 45-degree sine wave or something. So here's our curve c. C is also represented, C is going to be defined as our vector function, our parametric vector curve, r of t. And you'll notice that it lies on the 2D plane. So in other words, this curve doesn't jump out into the f of xy direction, because this is the scalar value for each ordered pair on xy. But this curve, we're going to write it in terms of r, which is going to be in terms of just x and y, x of t and y of t. Okay, now the idea here is, though, could we find the area between the curve and the scalar values for each point on the curve? And so to do that, conceptually, we'll look at the height of the curve at point A. We'll start at point A and we'll go to, let's say this is point B. And so we're going to look for every point along the curve. We're going to find some height associated with that ordered pair, some scalar value associated with that ordered pair. And as you'll notice, each point on the curve is going to have an associated point on the scalar surface. And so when we can join all of these, what we end up with is a surface. It's a curved surface, but a surface nonetheless. And so just like with regular integration that we've spent a lot of time doing in Calc 2 and Calc 1, you'll notice that we could actually turn these into little rectangles. We could cut them up into rectangles. And so the idea of a scalar line integral is finding the area under the curve that is related to the surface of the scalar field, f of xy, and also the parametric curve that is going to just live in the xy plane. And so we'll talk about how to do that next video, and then I'll give you just a quick idea of what a vector line integral looks like. So with a vector line integral, we are going to live in a vector field. And what I mean by a vector field, I'll just do a 2D vector field, is that every single point on the xy plane has an associated direction and length. And so, it's going to take a while to populate this, but I think you probably can see the point, is that every ordered pair on this xy plane has a vector associated with it at that point that has a certain length and a certain direction. The idea of a vector line integral is, what if we put our, I'm going to use blue for this, what if we put our r of t, our parameterized curve, what if we have it going through a vector field? Now the idea of this is going to be, what we're going to be looking for is we're going to look at an infinitesimal point on this curve. Let's take a look here maybe. And what we're going to look at is, at this point on the curve, where is the vector function, the vector field, where is that pointing? So maybe in this case it's pointing in this direction. And so what you have here is a change in r. So in other words, our vector function r, which is pointing from the origin to the curve, is changing infinitesimally. And as that occurs, what does the vector field look like next to it? So this is going to be called dr, the change in the function r, and that's a vector. And then this is going to be our vector function. I'm going to call it capital F. And what we want to do is we want to figure out how much of f goes in the direction of dr. So in other words, we're going to do a dot product between f and dr, because we want to multiply how much of f goes in the direction of dr. So that's a dot product. And so what we want to do is we want to integrate the vector function dotted with the parametric equation of curve. And we'll do it from some point A to B. And so this is kind of the basic form of the vector line integral, and we will go into a lot more detail over the next two videos. I'll see you then.